Hey everybody, today what we're going to talk about is a particular property of a relation, and you can see the title up on the top. What we're going to talk about is functions. And in grade 9 you were introduced to relations, you ended up working through equations of them, graphs of them, and so on. Today what we want to do is we want to talk about a special type of relation, that being a function. So what you see on your screen right now is, I don't know if you want to call it like a rough definition of it, but really a function is a relationship in which one quantity depends on or determines or corresponds to another. Now, that statement really refers to any relation, the way something relates to something else. A function adds in an additional property. For us to talk about that, we need to go back and talk about some grade 9 stuff. So let's jump into some more review. So what you see on the screen right now, those 3 bullets on the left, those all define the parts that make up a function. Now, one of this is very particular to being a function. The rest is just a generic relation. So when you take a look at that first bullet, and you see that we have a set of inputs. And those inputs are called the domain. Now, in grade 9, you were introduced to the term domain, and we remember that those are our inputs, and generally, so for a generic relation, those inputs are our x values. So you pick your x, your independent, and you sub it into your function. Okay. The second bullet, it's a rule. And when you see the word rule, I don't know if that really kind of sticks with us, if it's not what we're used to seeing, what we normally see. But that rule is what you refer to when we take each input and it determines the output. Now, you'll notice that it says, by which each input determines one and only one output. I want to come back to the one and only one part because that's key for a function. However, the rule you just got used to calling, well, your equation. Okay, last bullet. We talk about a set of outputs. Your outputs is called the range. That is review from grade 9. We just remembered that for a generic relation, we're talking about y values. So, as an example, if I ended up giving you a y value being determined by x's, then if you looked at that orange relation that I just put on the screen, the x would be my domain. So if I picked a series of x's, or if the problem restricted the values of x that I could use, my equation is really my expression. So notice, my equation looks like 2x plus 1. That's my expression. But it's also my rule. What that rule would say is, take your x value, double it, and add 1. That's what that looks like as a rule. Double your x values, add 1. All of that now spits out a y value. So if I take my input, I put it into my rule, I do whatever it says, then when I calculate that, it's going to spit out a y value, an output. And there's how our relations work. Okay, the part that I said was very important for us. Look back up at the second bullet, the one and only one. That is a key feature of a function, not just a generic relation. So I want to zero in on the one and only one. Okay, you can see up at the top left, this is us addressing the one and only one. Okay, I want to talk a little bit to make sure that we are good on the one and only one. What that means is each input determines exactly one output. Okay, exactly. Not 2 or 3, exactly 1. That's another way of saying 1 and only 1. Okay, so what does that mean? That means if I sub in one x value, then it creates one output, one y value. Now, you might look at it and you might say, okay, why are we going into such detail? This seems pretty straightforward. Look at the stars on the next line. Where it can get confusing a little bit is that different inputs can produce the same output. So to make sure that we are good, I can have an x value that only determines one y value. So when I sub an x into my equation, I get one and only one y value. But I could sub in different x values that all give me the same output, the same y value. So let me just put down a quick little picture in the top right corner so that we can kind of make sense of that. On your page, what I want you to do is put down a quick set of axes. I want you to kind of come along with me on this one. Okay, I want you to imagine that we have this relation. And if I choose an x value, let's say 1, and I sub it into my relation and I calculate my rule, I do whatever it says, and it spits out an output of 4. That's what it means to have the point 1, 4 on your graph, on your relation. Okay, let's say that I pick a different x value. Now maybe an x value of like -3. And I sub it into my equation, I follow my rule, and it spits out the same output, 4. That is okay. That's what we're talking about here when we say different inputs can produce the same output. No problem. Totally acceptable. No problem. Okay. However, what if now I go and take an x value, and let's say it's an x value of 1, and I sub it into my equation, my rule, and I follow my rule, but now it spits out a y value of -1. That is not okay if we're talking about a function. When I sub in an x value of 1, I get 2 different outputs. Look up in my graph. I got a 4 and I got a -1. That means that that's not a function. It's just a relation. So how can we sum up what we just had on our picture? Look at the last little statement. Therefore, a function can have points that are across from each other. Look at my red points, no problem. But you can never have points that are above each other. Take a look at my 1, 4, and then my blue point. That could not happen when we talk about a function. Okay, for the next couple years, you guys are going to talk about functions in detail. For a lot of you, your grade 11 course that you will select is going to be called functions. You may end up taking the course after that that's called advanced functions. Like, functions are going to become an important part of what you address. We spend a lot of time talking about functions. We spend a lot of time talking about how you can tell the difference between something is a function or not. But we don't always talk about why it matters. So I want to take a quick moment to talk about why it matters. So what you see on the screen now is an example of a function. So when we talk about a function, I'm going to just use an example of income taxes to show you why a function matters. Income taxes and the way income taxes work is a function. In fact, it would require it to be a function. If it wasn't a function, it wouldn't exist. And I'm going to argue that probably a lot of what you've encountered in your day already today depended on income taxes. You know, you walk out of the house, you walk down the street, you're on a sidewalk, that's getting paid with taxes. You hop on a road, taxes. If you took a bus to school today, taxes. You're attending a public school, that is taxes. A lot of what we've addressed in our life comes from taxes. So why is it important that it's a function? Okay, let's take a look and break down the components of that function if we talk about income taxes. The first thing, our input. You see that in purple? Our input would be someone's income. So how much money did they make in a year? The second thing is the rule. That would be our tax laws. So Canada Revenue has a set of tax laws created by the government. We would follow those tax laws. And then our last bullet is our output. Our output would be the amount of tax you pay. So what happens is you take whatever amount of money you made at the beginning of the year, you now put that into all of your tax laws. And it is now going to whip through everything. And that's just me like having everything's going through the machine. You calculate all your deductions. You figure out how much you paid in certain areas and whatever. And then when you calculate it, it is now going to spit out your tax. Okay. I want you to understand why that is a function. Let's say that I made a certain amount of money in a year. So let's say, nice round figure, I make $100,000 in a year. I now take that and I follow all the laws. I'm not talking about breaking the law. I follow the law. And if I claim all my deductions and everything that I need, it is now going to spit out an amount of tax that my purple has to pay, my $100,000 person. Okay, but what if someone else makes a different amount of money? So let's say that when they work their way through, they make $90,000 in a year, $80,000 a year, just a different amount of money. Then if I follow all my tax laws, same thing, maybe I can claim different deductions. Maybe my personal circumstance allows my equation, my rule to have me claim different things. Then it comes down and it spits out the exact same dollar amount. Notice they're both in purple. That is okay. That happens a lot. No problem. The system doesn't break down. Everything's good. We both pay the same amount. So maybe both those people pay $30,000 in income tax. No problem. I want you to picture a different scenario though. What if my $100,000 person, the exact same person, now files their income taxes? And when I filed my income tax, it came down and it spit out a different dollar amount. Okay, we have a problem. Now, what I want to do is I want to put dollar amounts to this so that it makes sense. Go back to my $100,000 person the first time. When I spit out, or when I follow all of my tax laws and it spits out my income tax payment, that's going to be $30,000. Very reasonable. But let's say it also gave that same person, okay, the exact same person, an option of paying $1. Which option do you think the person's going to choose? Like, I like to joke that, okay, everybody is so civically minded. We're all going to take the hit for the better good. Yes, we would all agree we'll pay the 30. No way. Every single person in here is going to pay the buck. And if everybody chose the smaller amount, which probably everybody does, then there's no way any of these things that we're talking about you dealing with today are ever getting paid for. The only way our tax system works is that when it spits out your tax bill, it spits out one value, not options. Okay, that might seem really abstract because most of you don't pay income taxes. Like, yes, you might lose some taxes on your paycheck, but you don't make enough in a year that you don't get it back. You probably all get it back. The first function you dealt with in grade 6. There is your bed mass. You've been working with functions since then. I want you to imagine how weird it would be if I gave you a problem and I said, what's 5 plus 3 times 2? And you told me that you could get an answer of 11 or 16. Well, I just pick the order that I do my stuff in. So like I can pick either order. They're all good. No, you can't do. Think about that mathematically. The fact that when we take an expression and we calculate it and we get one answer only, we've defined a rule called BEDMAS that gets us that one answer is so key. So that has been your experience with functions, and that is why functions are so important. I hope that gives us a little bit of background. Okay, I want to change gears a little bit, and we need to talk about some notation. So I want to kind of go back and talk about something that you were introduced to back in probably about grade 6 or 7. But we got to talk maybe about a different way to write something. Okay, bottom of your page. I want you to notice that what we have at the bottom is a discussion real quick about interval versus set notation. Okay, what I've given to you across the top is all of your set notations. And what you'll notice in each one of those sets is there's our good old greater than, less than symbols. I am going to bet that for a lot of us, there is still a little bit of indecision at times on what those inequality symbols represent when we write them. Like that is, what is a greater than symbol? Like a lot of us would say that's a greater than symbol, but it might not be. It depends on the order we read. So if I wrote x is greater than 5, then yes, if I read that left to right, that inequality is a greater than. But if I read it right to left, then that's 5 is less than x. It now became a less than symbol. It depends on the order in which we read. Because of that, I'm going to bet and say there's a little indecision, and I don't know, do you still go back to the alligator that eats the bigger thing? I don't know. What I want to talk to you about is a different way to write that, and that as you get older, you're going to probably see interval notation pop up even more. So what is interval notation? So what I'm going to do is I'm going to talk about taking a set notation and writing it in interval notation. So you have a couple of examples for us to go through. First off, when you read that set notation, we always read variable out. Variable out. So if I want the first part of that statement, I would read that starting at the x and then going to the left. So x is greater than or equal to -2. What that makes is my -2 my lower limit. That is the bottom of the acceptable range of values. X has to be greater than or equal to -2. That makes -2 the bottom of what's acceptable, my lower limit. So I put a -2 on the left. The left side is always my lower limit, comma. And now I notice that x has to be less than or equal to 5. So my 5 goes on the right side, and what that 5 represents then is my upper limit. So in interval notation, what we have is okay, my variable, my x, has to be between those values. So in interval notation, we state what it has to be in between. Lower limit on the left, upper limit on the right, and we are good. There you go. Okay, there was something in particular that I skipped over that I'm hoping my example for x is greater than 7 will show us. Okay, how do I write x is greater than 7? Well, the first thing I need to address is x is greater than 7. So 7 is a key value. Either side of 7 means I'm included or I'm not included. So the first thing I need to figure out, is 7 an upper limit or a lower limit? Because it says that x is greater than 7, then that means 7 must be my lower limit, so it has to go on the left. Okay, we may be tempted to do this now. And here's where I want to highlight one key difference. Notice when -2 was our lower limit in the first one, x was greater than or equal to it. But now in the second statement, when x is greater than 7, it's not also equal to it. So how can I tell the difference between those two when I write that down? Notice by me writing the -2 and the 7 the exact same way, I can't tell whether I'm supposed to include the value or not. Okay, here's our adjustment. I get rid of that square bracket and I write it with a round bracket. That round bracket means do not include. So if you were to talk to me about that, I wouldn't care whether you use the term square bracket or round bracket, or what you'll often hear of is a closed bracket to talk about the square one versus an open bracket to talk about the round one. I do not care what vocabulary you use. You're good either way. Okay, let's come back to the actual statement now. Now that we have a proper lower limit at 7, but not including it, that set notation says that x is greater than 7. So what that means is it doesn't stop. I could start listing out real values and keep going forever. So how do we denote forever? There is our infinity symbol. Now, key thing. As I'm trying to decide, do I put a square bracket? Do I put an open? Is it a closed or an open one? We need to keep in mind one big thing. If you recall from grade 9, you should have had a conversation about infinity. Infinity actually means without bound. It just means forever. So when you use the term forever, I want you to consider, can you ever equal forever? And I hope you say no. Like, I hope you're not going to say something ridiculous like, yeah, but what about like infinity plus 1? No, you cannot have forever. I can't equal forever. So a closed bracket is never an option on infinity. I always need an open bracket. I can never equal infinity. So if I just get rid of that underneath, and now that we've had that discussion, there would be the statement x is greater than 7 in interval notation. You would say 7 to infinity. Okay, let's jump in on the last one. The last one kind of throws everything together. You take a look at your inequality symbol, and if we're talking about values for x, then we're talking about less than or equal to 3. Okay, less than or equal to 3. Does that make 3 an upper limit or a lower limit? Well, if x is always less than 3, then 3 is my upper limit. That means it goes on the right. Because I have an equals to in that inequality, I need a closed bracket on my 3. Now that says go up to 3 and include it. If x is always less than 3, then that means I go forever less than 3. Well, the forever part brings us into that infinity again, except if you notice, I'm going in the opposite direction. Like I start to talk about integers, for instance, like 2, 1, 0, -1, -2. You'll notice I'm going to go forever negative. So my lower limit then is negative infinity, forever negative. Okay, we shouldn't have an issue with the bracket. We know we can never equal forever. There's our open bracket and we're good. Okay, my promise to you, I will never, ever, ever prescribe which one of those notations you have to use on an evaluation, ever. If you want to use set notation, feel free. If you want to use interval notation, feel free. The only issue is you have to be able to read and interpret both. So I have no problem giving you set notation or giving you interval notation on an evaluation. It's up to you to make sure you can interpret it. But you can write your answer in any form you like. Okay, I want to change gears now. So we talked a little bit before about what it takes to be a function. I want to talk about some parameters with that. Some, if given in a certain way, how can we consider it? If given it, we're going to change gears a little. Here we go. Okay, what you see on the screen right now is a lot, I'll give you. But I want to go back to our discussion about what is a function. So if you notice back up top, we're talking about it's a rule, and it's a rule for generating a value with respect to a variable. So if we go back to our definitions from before, you would have taken your domain, you would have subbed it into your rule, it would have spit out a value. There we go. Why I'm talking about that is because I need us to be very, very clear on what we talk about when we say the value of a function. And can you please make sure that you underline that the same way as what I did? Because there will be times where I'll say, well, hey, what's the value of that function? And you may be tempted to look at a coordinate and say, yeah, but like which value do you want? Do you want the X or the Y? And I'm going to tell you, well, I've been very clear. I've asked for the value of the function. You need to know what that's referring to. So since our equation is a rule for generating a value given a variable, the value of the function is the Y value. It's the output. I get to pick my X value. I plug it in, or the circumstances pick my X value. We plug it in. But the rule generates the output. So my output is always the value of the function. Okay, now that we've got that clarified, then I want to come back to the question about us. How can you tell if a relation is a function? And I'm going to argue to you, it all comes back to that one definition of each input gives one and only one output. The idea that we can have points across from each other, but we can't have points above, that one X gives one Y and only one Y. Well, that can look a little different depending on how the relation is presented to you. So what you see in the ordered numbers down the left, those are different ways that a relation could be presented. So take a look at 1. When we look at 1, the first way maybe that I could give you a relation is a set of ordered pairs, a list of coordinates. What you see after that dash is what we want to think about as we're trying to answer the question, is the relation a function? So if you look in blue on that first line, does one X value have only one Y value? If it does, you know you're good. It is a function. If you can find an X that has more than one Y value, then you know it's not a function. Okay, let's take a look at number 2. When we look at number 2, maybe I give you the relation as an equation. I give you the equation of that relation. I'm going to argue to you that I think that that is the most difficult way to have to determine whether something is a function. So how do you do it? Take a look at the purple. The purple is a question that you actually want to ask yourself. And if you ask yourself that question, depending on your answer of yes or no, that'll tell you whether it's a function. So what I'm going to ask myself is, can an X value give me more than one Y value? So I start to imagine, well, if I subbed in a value for X, can I calculate 2 different values for Y, or more than one value? And if I can, then it is not a function. I need to make sure that one X gives only one Y. Okay, last one, number 3. I think that this one, if it's not the easiest, it's right up there with ordered pairs. On my graph, if I give you the picture to a relation, how can you tell? And there's something you see in blue there called the vertical line test. You're going to be very familiar with this. If you use a vertical line and you scan that vertical line across your graph, then if that vertical line hits your graph in more than one spot, it's not a function. The only way a vertical line can hit your graph in more than one spot is if we have points above each other. And we know that that means not a function. So if you can scan a vertical line across your graph and you never hit 2 points or multiple points, then you know, yes, it is a function. That's going to become a really dominant way of looking for whether a relation is a function. Probably your go-to, especially when you have a picture. Okay. What I want to do now is I want to start kind of going through that process. I want to start giving you a relation in different forms and ask you to be able to go through, can you tell whether that relation is a function? Okay, let's jump in. Here we go. Okay, problem 1, take a look at the instruction. Is it a function? So you'll notice that I've given you a set of ordered pairs. There are my coordinates. I want to know, is that relation, if I went and plotted those points, would it represent a function or not? And so you could go through and produce a graph. And you could start plotting 2, 3, 4, 5, 6, 7, 8, 9. And you could plot those points, and then you could use the vertical line test. And you could say, well, okay, if I was to take a vertical line and start to move it across the page, like literally start to move it. So now the vertical line's here, it's here, it's here, it's here, it's here, it's here. Would I ever hit any of those red points more than one time? Let me reword that. Would I ever hit more than one of those points with one of those vertical lines? The answer is no. I'll only ever hit one of those points. Therefore, it is a function. Now, I'm going to argue to you that's a lot of work. And it's way more work than what's needed. If you take a look back up at number 1, well, it says if I have a set of ordered pairs, do I have an x with more than one y value? So the first thing I would do is scan down all of my x's. Do I see any of my x values repeating? I don't. So each x only has one individual y. Therefore, yes, it is a function. Okay, couple quick things. Don't get alarmed by me just looking at the x's for right now. If you were like, yeah, but wait a second, like my first point is at 2, 3, looking at the y value. What if the next point was at 4, 3, not 4, 5? I have the same y. And I say, who cares? Remember, 1x of 2 gave me a y value of 3. A different x value of 2 gave me a different, or the same y value of 3. Points can be across from each other. That's okay. I did not have an x value that gave me multiple y values. So I am good. I just have to look at my x's. Okay, let's walk through B. I start to scan my way down and I say, okay, 6. Hold up. That's where I stop and I say, I have 2 points that both have the same x value. So now I look at the y value that comes with them. You notice this time 6 gave me 2, another time it gave me 4. So if I have an x value of 6, my y values are 2 and 4. That means 1x gave me multiple y's, therefore, no, it is not a function. So I hope you can see when we have coordinates, don't worry about producing a graph. We don't care about that. You just scan your way across your x values. If you have multiple x's, consider your y's. If you now have multiple y's, well, then we have a problem. Okay, I'm hoping that clarifies that little discussion earlier about when we have ordered pairs. Now I want to jump into the difficult stuff. Now I want to start getting to equations. So you take a look at problem 2, and problem 2 says, is the relation a function? But I have put in here, do not graph. And the reason I want to put that in is because I want us to avoid using the vertical line test. Now, I'm going to put in 2 graphs for this, but I just don't want us to rely on the vertical line test because you won't always have the graph at your disposal. So I've put that instruction in, even though I'm going to use some graphs, and even though you could use some graphs for that, you would just run out of time. Okay, let's take a look at A. I'm going to talk about A with respect to its graph. So I'm breaking the rule right off the bat. But the reason I'm doing that is because you should have a lot of experience with A, right? There is my line, and you should all be comfortable to say y-intercept of 1, slope of 2. So if I was to produce the graph for that, I would get something, I don't know, like that, like a really sloppy sketch that's not meant to be a curve. That's just me not using a straight edge. Okay, I want you to take a look at that line. What does the vertical line test look like? Well, I hope you can see that if I was to put a vertical line down anywhere on that picture, I will never hit that red line twice, ever. So yes, it is a function. Okay, why did I want to talk about graph even though I said do not graph? Well, it's because I think that gives you a walkthrough on vertical line, but now it'll confirm for you when we don't use the graph. So my answer is yes, it is a function. We just need to forget that for a second. Okay, I also want you to forget that it's a line. The piece of advice that I gave you was to ask yourself the question, when you replace that x with a number, is it possible to follow the rule, do all the calculations, follow the equation, and have it give you multiple y values? So I want you to imagine you're going to replace that x with a number. Like I'm just going to pick a number. Let's just say I pick a nice easy number of 5. Now, what the rule says is it says take 5, double it, add 1. That's how I get my y value. Take my x, double it, add 1. Well, can you think of any x value you could sub in that when you double it and add 1, you're somehow going to get 2 different answers? I hope not, because there isn't one. If you pick an x and you double it and add 1, it is going to spit out one answer and one answer only. Therefore, yes, it is a function. Notice we didn't need the graph to do it, but it is more abstract. You have to consider some of those operations. Okay, let's take a look at B. Look at the operation in B. It's squaring something. So if I said to you, pick an x, sub it in, square it, is there ever a time where now it's going to spit out multiple answers? I hope your answer to that question would be no. Every time I sub in a number and I square a number, I get one answer. Therefore, yes, it is a function. Okay, why did I want to talk about this one? I'm going to talk this one about graph. We have not addressed this function yet, but we will. And this graph is going to become one that should be put in your back pocket. You're going to need to know it cold. That graph is a parabola, and it looks like this. Notice, if I pick an x value of, let's say, 2, and I sub that in, 2 squared gives me a y value of 4, I would have this point here at 2, 4. If I picked an x value of -2, -2 squared also gives me a positive 4. I get my points across from each other, which are totally fine, but I will never get points above each other. So yes, it is a function. Okay, I want to jump into C. C is one where we may be tempted to say, okay, if I pick an x value and I sub it in, and now I take the square root of it, can I get multiple answers? We may be tempted to say, yes, you can. You can get multiple answers because I know when I take the square root, that means a plus or a minus. And I want to go, great thinking, but incorrect in this situation. Okay, why is it incorrect? I want to make sure that we can tell the difference between whether you have the equation y equals root x or you have the equation y squared equals x. Okay, to do that, I want to make sure that we kind of go back to something. If I asked you to calculate what is the root of 4, then I hope you would tell me it's 2. Root 4 is 2. Like, we've spent time reducing radicals. You're good. Root 4 is 2. The difference would be if I had an equation where I said something squared equals 4. And now I asked you to solve for x. Well, then you would go, well, I need to get rid of that squared. And you are choosing to take the square root of 4. When you choose to take the square root, it could be plus or minus. But if you look back at the original one I gave you, there was no sign out in front. And no sign means positive. It doesn't mean plus or minus. So when you have the root operation written there, it is only the sign that's out in front, the sign of the term. But when you choose to take the square root, like we do in the red, then you could get plus or minus. So if you took a look at my red equation off on the right, if you wanted to isolate y, you would take the square root of x, and because you are, then it could be plus or minus. And I hope that you can see, because of the plus or minus, you're going to get 2 terms, the positive number and the negative number. So y could be 2 things. Therefore, that is not a function. No. But if we go back to the equation I gave you, you'll notice it's only the positive out in front. So when I choose an x value and I sub it in, I am just calculating the root of it. I will only get the one answer. Therefore, yes, it is. Okay, I think that one can get a little ugly, a little confusing, and I'm hoping that we're able to work our way through that confusion. Okay, last 2 problems. Okay, you take a look at the last 2, and I'm just going to shrink my screen a little bit. There is D and E. Well, you take a look at D, and D's got an ugly fraction in it, but remember, all we're trying to do is answer the question, is it a function or not? So look at the operations within the rule, within the equation. You are going to pick an x, you're going to sub it in. BEDMAS is going to say, subtract 2, that'll get you an answer. Then you have to take 1 and divide it by that answer. Okay, if I do those operations, is there any way that I can get multiple answers? I hope your answer is no. And since you only get one answer, therefore, yes, it is a function. So ugly fraction doesn't mean ugly. No, it's operations. Okay, let's take a look at E. Now, E is a graph or a relation that we should be very familiar with. Very familiar with. I'm going to ask you to tune that thing out right now. And now I'm going to talk about it. So, from a graph standpoint, we should be very, very good, given where we've come from, that that's the equation of a circle. In particular, it's a circle with center 0, 0 and radius 4. So because of that, I would hope that you can take a look right now and see that that circle is not going to pass the vertical line test. That if you were to go and take, and let me just slide that over, any vertical line and extend it in all those spots over that circle, you're going to hit that graph in 2 spots. And therefore, that is not a function. So the answer is no. Okay, if you recall back to our instruction, I told you to forget about the fact that it was a circle. So we have that in mind. Now what I want to do is get rid of the whole graph. Okay, if you were to look at this just from an algebraic standpoint and you had no clue that that was the equation of a circle, how could you come up with whether it was a function or not? Well, you'll notice that in my other graphs, it was a lot easier to tell whether something was a function or not based on isolating y. So maybe what I'm going to do is I'm going to get that y all by itself. So first thing I might do, get rid of my x squared, so I'm going to subtract it. The next thing I would do is get rid of my squared. So that means I have 2 possible answers because I am taking the square root of 16 minus x squared. Okay, BEDMAS, we should all be good that you cannot take the square root of the 16 and take the square root of the x. We're good on that. I shouldn't even have to talk about it. Repress the memory of ever seeing that blue. Okay. Now that you look at that equation, I hope that you are good to be able to tell that no, that is not a function, because look at your plus and minus. As soon as you have that plus or minus there, then whenever you sub in for x, when you take the root of it, you're now going to get the positive case, the negative case. There's 2 answers, therefore not a function. Okay. Where you really want to come from today's lesson is make sure that you're good on understanding the components of a function. If you got an idea of why functions matter, that's great. I hope that you're good with some interval notation, but we'll get a lot of practice with that over the course of the next unit and the next couple years. And finally, can you tell whether something is a function or not from ordered pairs, an equation, or the graph? Okay, your job now. Jump in and get some practice. Best of luck.